Yes, hello to everyone. So let us begin this new session with Marcelo Oyarzo. He's a PhD student from Universidad de Concepción and Politécnico de Torino. And he will be talking about black holes in the STU model of gauge B equal 4 n equal 8 SUGRA. So thank you very much, Marcelo. And you have 20 minutes.
Okay, thank you very much, Mariano. Thank you also to the organizers for allowing me to give this talk, and also for organizing all this meeting. It's a very nice meeting. Okay, so I will talk about black holes. Particularly, I will talk about the stability of black holes in this STU model. That this is a work in progress with Andrés Anabalón, Stefano Maurelli, and Mario Trillante. So the plan for this talk that I have in mind is give some motivations first. Then I will introduce the STU model of the D equal 4 gauge supergravity. And then I will give an example, a simple example that will capture an idea that I want to stress that will be useful for the rest of the talk. And the second part, I will talk about the stability of electric black holes in the STU model and of what happened with magnetic black holes in that case. Finally, I will conclude. Okay, so the first ingredient that I need is that in supersymmetric theories, they have a symmetry generated by a fermionic parameter. So by virtue of the Nether theorem, we will have some supercharges, some conserved charges that are integral in a codimension 1 surface. And then if you compute the Dirac bracket between the supercharges, you will find that they closed on other conserved charges as usual, plus a possible central extension. Okay, so what I want to stress at this point is that this superalgebra will imply in general a bound on the energy. So the energy will be bounded from below, and the equality will hold for the vacuum state of the configuration. So now, what happens if we add we go to a supergravity theory? Well, many things will happen, but in particular, this is means gauging the supersymmetry. So you will have a theory which have this invariance under a parameter that depends on the point. And one of the consequences of this is that the supercharge will be an integral in a codimension 2 surface, because this Hoche star of the Nether current can be written as the exterior derivative of something up to the equation of motion. Okay, this is the general idea. And then one can compute indeed the bracket between the supercharges. And this was done by Christoph, Toldo, and Van Doren years ago. And the general result is that it is given in terms of the super covariant derivative of the Killing spinor, which is nothing but the variation of the spin 3/2. Okay, so you can compute that, and then you can compute the bound at the end. So let me define so what is a supersymmetric configuration, as was already introduced by Anageli. Is a configuration that satisfies that the variation of the fermionic fields equal 0 have a solution, non-trivial solution, for the Killing spinor that generates the supersymmetry transformation. And this will define you whether your configuration can or not saturate the bound. Okay, and these matrices here, the bold matrices, are in general function of all the fields, the metric and the matter fields, the scalars, if you have the vectors. So the statement regarding BPSness is about the full configuration, not only on the metric, even though the spinor is called usually Killing spinor, the solution of this is. Okay, the problem is that in supergravity, there are BPS states that are naked singularities. This is quite a problem because you expect that your vacuum state is a good state, no? It's a say well defined. This is the first observation that I want to make, and the second one is more well known: is that the black holes are thermodynamic objects. Okay, so they have an entropy given by the horizon area divided by 4 and a Hawking temperature. Okay, and this is at the leading order. And so in this context, the question regarding stability of the thermodynamic system is well posed. So you have a black hole, you can ask whether it is stable or not in the thermodynamical sense. And in particular in ADS, in black holes that are asymptotically anti-de Sitter, they have shown to have this Hawking phase transition between black holes and the thermal ADS. And also in holography, these have a really interesting interpretation. Okay, so with these two ingredients, I want to play a bit with black holes in the STU model that I will introduce now. Okay, so the STU model is defined as a truncation of the maximal theory in a certain way, and at the end of the procedure that I cannot give all the details here, but ends in a n equal 2 gauge supergravity, which general Lagrangian is given by this, where you have some scalars parameterizing your scalar manifold. And in this case, in the n equal 2 theories, you can have well, a special Kähler manifold or quaternionic. But in this case, we don't have quaternion. With quaternionic manifold, you have only the special Kähler one. And this manifold has certain properties that allow you to compute the vector, sorry, the scalar potential and the coupling between the vectors and the scalar through these matrices. And the gauge vectors are 4 in this case. So we have 4 vectors. Then the duality group will be SP8. And the gauging is done by Fayet-Diopoulos terms. In this frame is completely electric, and all the gauge couplings are equal. Okay, so this is the model that can be embedded in n equal 8 up to some subtleties that I will not enter in those details because there is not a unique way to do it. Okay, so in essence, we have this this picture. There is the n equal 8 theory. Then you can truncate to the STU model by retaining some singlets of an SO2 cube. And then you can keep truncating the model by identifying the gauge vectors and setting to 0 some gauge scalars, or identifying certain scalars. And you can end in a consistent truncation called the T truncation and the TQ truncation. But also you can turn off the real part of your complex scalars that I wrote here. As usual, they are parameterized by this chi, which is called an axion field, and phi I, that are the dilatons. So if you turn off the axion, you will end up in a theory which is called purely dilatonic, that can be embedded in the STU back if you satisfy a constraint. So it's not in the same footing as the T and the T cube. Okay, and all these theories can be reduced to the minimal gauge supergravity n equal 2, which is Einstein-Maxwell with negative cosmological constant, essentially. So I will give you an example in this theory, in the Einstein-Maxwell with negative cosmological constant. And the example is the ionic Dresden-Nordstrom ADS. So there is I will consider the spherical case. So we have a parameter, which is the M, which in this case is the mass related to the mass. Q and P are the electric and magnetic charges. So this is the gauge vector. And one can ask, okay, can I satisfy the BBS equation by fixing these parameters M, Q, and P? And this question was answered by Romans in 1992. And the answer is that there is 2 options to do that. The first is setting to 0 the magnetic charge and fixing the mass in terms of the charge. And the second option is killing the mass, but fixing the magnetic charge equal to a constant related to the gauge coupling, or the ADS radius, if you want. And these 2 configurations preserve some amount of supersymmetry, and but they are naked singularities. And there is one aspect that I want to stress here, is that asymptotically, these 2 configurations are essentially very different. Because in the electric case, you have there is no magnetic charge, so everything goes to ADS 4, while in the magnetic case, you have this magnetic non-trivial charge here, and therefore it is asymptotic to ADS with this extra gauge field. Okay, so one question one can ask is, can we resolve this singularity problem in some way? And the answer is yes, people have done that. One way is adding rotation, so you can have rotating BPS black holes, or you can change the geometry of the horizon by putting an hyperboloid instead of a sphere. In that case, you can save the day. Okay, and what happened adding scalars? Well, then people have constructed the solution of this that was done by Duff and Liu with 4 electric charges or 4 magnetic charges. And 12 years later, Cacciatori and Klein showed that indeed you can have spherical black holes, supersymmetric black holes with magnetic charges. Okay, and indeed one can show, and this is what I want to, among other things, what I want to show is that these two things are equivalent at the end of the day. The Duff and Liu and Cacciatori and Klein are the same configuration when they are reduced to the same theory. Okay, so now I will move to the work that we are doing with Andres and Mario and Stefano, that is regarding stability of these kind of black holes. In particular, I will concentrate on the Duff and Liu. So let's start with the electric case. So the gauge fields are only electric here. And there is a integration constant, which is small m here. There are some other integration constant, small q lambda, that are this constant entering these harmonic functions. The zero of the harmonic functions will fix the point where the manifold is singular. There is a curvature singularity where this vanishes. And the scalars are ratio of these harmonic functions, and the magnetic charges, the electric charges q lambda are fixed in terms, must satisfy this constraint between the small q's lambda and m. And this q volt, I will call it, was introduced by shifting the radial coordinate and allow to study a little bit better the BPS limit. Okay, so the BPS limit of these configurations are, again, naked singularities, and they must satisfy this constraint. But okay, that is what happened if you want to have a killing spinor. But if you don't, imagine that you want to consider a more general configuration. You know that there is this configuration that saturates the bound. So let's consider again the general configuration with planar horizon. Okay. So what happened is that one can solve the parameter small m in terms of the horizon area that I will call capital A, and the electric charges that I call capital Q lambda. There are 4 of them. And this is nice because if in this case it's happened that the small m is the energy of the configuration. Therefore, you can compute the derivative of the energy with respect to the entropy and the charges, and you will reconstruct the first law. You can compute the Hawking temperature and the chemical potential that allow you to have regular gauge fields at the horizon in the Euclidean version. Okay, so one can study the stability of these black holes. Okay, and what happened is that you can study the Hessian matrix. And what happened is summarized in this proposition that I will show to you, is that all electric planar extremal black holes are thermodynamically unstable. Okay, and the proof goes as follows. You know that the energy is given by this expression that I didn't show you how it's derived, but it's true. Then you compute the second derivative with respect to all the parameters that you have, the horizon area and the electric charges. Then you get a 5x5 Hessian matrix. So you in general cannot find the eigenvalues in a closed manner, no? But what happened is that the determinant can be written in a simple way in terms of the Hawking temperature. Is this expression here minus essentially the sum of the electric charges squared. So you see that if the temperature is 0, for sure this is negative, and there exists at least one eigenvalue that is negative. So this proves this statement. So now let me move to the magnetic case. The magnetic case is generated by using the symmetries of the scalar manifold. In particular, you can rotate the scalar in certain way that the electric vectors become magnetic, and they are a solution of the equation of motion. But the BPS conditions are different. This is what happens when you do this kind of electromagnetic duality. And the configuration is almost exactly the same. Just the vectors are magnetic now, and the scalars have this minus sign, but this is the only difference that are here. So this is the magnetic planar KD black holes. So now, what happens if we impose the BPS condition? Well, what happens is that the magnetic charges must satisfy this condition here, which is known as the topological twist condition. And the parameter M is fixed in terms of this M BPS that I call, which is nothing but a function of the P lambda, the magnetic charges. And this omega is just a matrix with -1 and 1s around. And due to that, the metric function factorizes in a perfect square. So any black hole configuration that you find in the BPS limit are indeed extremal black holes. So this is good. It's a good configuration. Indeed, this is kind of what Cacciatore and Clem found. Okay, so now there is a tension here. There is a tension because the BPS limit is extremal, and it is it's the BPS configuration. But we have shown in a very similar configuration, but electric, that those configurations are unstable. No? So this tension indeed can be realized in a more sharp way, because indeed you can solve again the small m parameter in terms of the horizon area and the magnetic charges. So you can run the argument again and say, okay, these are unstable. But this is a contradiction, because the BPS state should be a stable vacuum state, because it's a black hole, a zero temperature black hole. One expects that this is good. Okay, so, but we are not sure that this M now represents the energy of the configuration. So to save the day, we will propose an energy that is this function here as a function of the area and the magnetic charge, plus another M tilde that depends only on the magnetic charges. And this is so because we want to preserve the fact that this M realize the Hawking temperature if you compute the derivative with respect to the entropy. Okay, so it is not so bad. It's almost good.
Marcelo, you have 3.
So what? Let me finish then. What we do now is trying to connect with the BPS configurations. So for that, one can ask when the asymptotic killing when there is an asymptotic killing spinor. And the answer is that indeed you can have asymptotic killing spinor if and only if your background satisfies the topological twist condition. Okay, and this happened, but I didn't fix a small m yet. So a small m is arbitrary. So you do that, you solve your asymptotic killing spinor, and you get two of them, one with the plus and another labeled with a minus, where these plus or minus are related to the projectors that Anayeli was talking in the previous in the lecture. Each of them kill 1/2 of the full BPS. In this case, we are in n equal 2. Okay, so we now can plug in the Christoph formula for the commutator, the Dirac bracket between the supercharges, but on a background that satisfies the topological twist condition. So all this that is in purple is the supercovariant derivative, and we will evaluate this in the configuration that satisfies the topological twist, and we will do the sandwich with the asymptotic killing spinor. So we have two bounds in principle, one with the plus and one with the minus. So one goes through the full computation. There is the result is that the BPS bound is that this volt m plus minus must be greater or equal than 0. This is the BPS bound, where this m plus minus is defined as follows: is small m plus minus this mbps, that is the function that I define with this p lambda, is a function only on the p lambda. In particular, the bound for the plus, it works immediately because it's a product of sum of the squares, is true, while the m minus bound, this one, imply that the parameter m minus the mbps must be greater or equal than 0. So this can be a good candidate for the energy that allow you to conclude that the object, the configuration, the extremal configurations are stable. And the answer is yes. If you consider this as your energy, here I just repeat again what are these m and the mbps, a function of only on the piece. You can indeed satisfy the first law for certain chemical potentials that are modified due to the presence of this extra term. And now we can state the following proposition, and I will finish with this. The energy E has a semi-positive defined Kessler matrix for black hole that satisfy the topological twist condition. Okay, and I will not prove this, but I hope will be in archive in the next weeks. Okay, that is what I wanted to say. Just here I leave some future work that one can do, and I want to hear if you have some questions. So thank you very much.
Thank you, Marcelo.
Okay.
Questions? We have 5 minutes for any questions.
So I will start with the question. Well,
Yes.
Well, then I will start first, and then I leave Carlos. What this BPS twisted BPS condition? It's like
yes.
the same thing you do when you go from a supersymmetric theory to a topological theory, or it's something different?
Like you mean
what do you call it?
Yeah, in this case, I guess the let's say the translation to the field theory. What does it mean in the field theory side? Is precisely adding a background field, constant background field in the which is precisely along the direction that is turned on, like this one. Okay, so this because this is preserved even in the asymptotic region. So the dual theory in this case is the ABJM will have this extra background field turned on. So I think it's the same topological twist as people talk in the supersymmetric theories. I don't know if it is
what?
Tell me. No.
And this works for all conformally flat spaces or only flat? You are working asymptotically flat, right? Here.
This is asymptotically ADS, the four-dimensional configuration, but the constant T and constant R slides are planes. So the dual theory will be formulated in a Minkowski tree with this extra gauge field.
Okay, thank you.
Carlos?
You're welcome.
Nico Grandi was first. I
didn't see.
Vale.
Nico?
It's the same. Can you hear me?
Yes.
Can you hear me?
Not really well.
Wow. Okay.
Like your microphone.
Let Carlos ask, and then if I can fix my microphone.
Vale,
okay.
So Marcelo, let me ask you in this question, all very interesting, by the way.
Okay, thank you very much.
So suppose that you go to the extremal case, right? So zero temperature, right?
Yes.
And I have a black hole with a naked singularity, right? So I want, it's supersymmetric, right? So your first reaction is stable. But suppose that I do a fluctuation, right? And the fluctuation falls into the singularity, right?
Okay.
So,
but you have a horizon here, or
I see. Okay. So
this, do you have or not?
Okay, that will save the problem, right? So, but if there is a horizon, why you care about the naked singularity?
No, yes.
I'm thinking in the electric case.
Yeah, in the electric case, indeed, this I guess it was well studied in the past. The statement that electric black holes are unstable, at least in Einstein-Maxwell, and the extension in this direction of the STU model is quite well understood. But the idea, I think, is that if you have the black hole there and you perturbate it, it's likely it will go in some sense to the naked singularity configuration. But that is quite weird. So I really don't like too much that kind of processes, no? I would expect that we'll end up in another black hole that is, at least there is a horizon, no? I expect something like that. So
yeah.
I don't know, maybe start rotating or something like that that allow you to end up in a BPS state with the same boundary conditions, but with a healthy
non-singular, avoiding the singularity. Okay.
Yes.
Thanks very much, Marcelo.
No, thank you for your question, Carlos.
Thank you, Carlos. I think Nico says doesn't matter. I guess his microphone is not working very well. So we thank Marcelo again.
Okay, thank you very much again to the organizer. Thank you, Mariano. I will stop sharing.
And